In pursuit of sharing technical knowledge and to support new engineering entrants, I, Pranav, will be presenting today's presentation on Power Transformer Part 86. As the topic is of the continuation, so for your convenience, the link of the previous session is given under the description box. Let's start with distorting and weakening the internal field of transformer dielectrics under electromagnetic exposure. Electromagnetic waves interact with the dielectric insulation, oil and cellulose paper in transformers through three primary mechanisms. One, polarization. Number two, dielectric loss. And number three, wave propagation effects. Polarization is the alignment of a molecular dipoles under the influence of an alternating electric field, resulting in electric energy storage within the dielectric medium. Dielectric loss, energy dissipation due to delayed or lagging polarization response and finite electrical conductivity, resulting in energy dissipation in the form of heat, especially at elevated frequencies. Wave propagation effects, that is, reflections, refractions, and resonances within the transformer windings and insulation structures that can locally intensify electric stress. Polarization. High voltage transformers, while operate under the continuous exposure of electromagnetic stress, their internal insulation, primarily oil impregnated paper or pressboard, experiences constant dipole and interfacial polarization. Dipole polarization mechanism is entirely driven by the application and characteristics of an alternating electric field, which forces the polar groups in cellulose like hydroxyls and polar impurities in the oil to reorient continuously. The continuous polarization process that leads to constant cyclic alignment and realignment of dielectric dipoles to the alternating electric field. But as due to molecular inertia and internal friction, the dipoles cannot reorient instantaneously, causing to lag behind the alternating electric field. The continual phase lag causes energy to be dissipated as heat within the dielectric material, contributing to dielectric loss. The simultaneous increase of power losses that leads to continual increase of the transformer's operating temperatures. The condition would have become much more critical when the thermal agitation of the molecules tends to randomize the internal dipolar alignment, which thereby reduces the polarization effect but increases the baseline conductivity and leakage currents within the dielectric. Such happenings significantly degrade the lifespan of the oil paper insulation system. Constant interfacial polarization in high voltage transformers happens mainly because of their insulation system is configured with a heterogeneous composite dielectric system, that is insulating oil and cellulose paper and Presbo. Insulating oil and cellulose paper possess vastly different dielectric constants and conductivities. It is to understand that the relative dielectric constant K or relative permittivity epsilon R is fundamentally referred to measure an insulating material's ability to store electrical energy in an electric field compared to a vacuum. It is a dimensionless quantity and is rather to indicate how much a dielectric material reduces the effective electric field within it compared to a vacuum. From the fundamental relationship, dielectric constant K equals to relative permittivity epsilon R equals to E0 by E net, where E0 is the electric field in a vacuum for free space. E net is the reduced electric field within the dielectric material. Under the exposure to an external electric field, the dielectric material's molecules are thus to polarize, creating induced or aligned electric dipoles. The nature of this polarization depends on its molecular structure. In case of nonpolar molecules, where there is no permanent dipole moment. In case of nonpolar molecules, where there is no permanent dipole moment. However, the electron cloud within the molecules are being stressed by the exposed electric field, creating a temporary induced dipole moment. Temporary induced dipole moment. In case of polar molecules, where these molecules already have permanent dipoles, but they are randomly oriented. The external field exerts a torque that forces these electric dipoles to rotate and align with the direction of the field. This realignment of electric dipoles creates an internal bound charge that opposes the external field, reducing the net electric field within the dielectric. The molecules in a dielectric material that are to polarize when exposed to an external electric field, that is E0. The bound charges within its molecules are going to shift. Positive charges move with the field and negative charges move against it, creating internal electric dipoles. The internal dipoles essentially neutralize each other within the bulk of the dielectric, but some of the excess uncancelled bound charges would thus to accumulate on the inner and outer surface of the dielectric material. These accumulated surface charges generate their own secondary electric field, that is E internal, pointing in the exact opposite direction of the original electric field, that is the applied electric field E0, thus cancelling out a portion of it. This creation of their own electric field, that is E internal, is often called as an internal polarization field or depolarization field. The total or net electric field, E net, inside the dielectric is the vector sum of the external and induced fields, resulting in a net field that is weaker than the original field. Therefore, the relationship is expressed as E net equals to E0 minus E internal. From the fundamental relationship, the net electric field within the dielectric is reduced by a factor equal to the dielectric constant K. That is, so mathematically, it can be expressed as E net equals to E0 by K. That is dielectric constant. The relative dielectric constant or relative permittivity of the dielectrics are preferably prescribed for using as the power transformer insulation purpose. It is very essential for designing a power transformer insulation system. Transformer oil impregnated craft paper. The dielectric constant is 4 to 4.5. Transformer oil impregnated pasteboard 3.5 to 4.5. Dry or unimpregnated cellulose is 2 to 2.5. Last, transformer oil mineral or ester is 2.2 to 2.5. If a material has a dielectric constant of 4, it means the electric field inside that dielectric is 4 times weaker than it would be in a vacuum. Unlike general purpose transformers, power transformers are specifically designed to optimize for continuous operation under high voltage stress. High voltage stress in power transformers directly involves in driving the electrothermal stress, which is rather to create a destructive thermal dielectric feedback loop, often leading to thermal runaway. Most important, high voltage stress in power transformers directly involves in driving the electrothermal stress, which is rather to create a destructive thermal dielectric feedback loop, which is which is often leading to a thermal runaway. Transformer, while facing an abrupt voltage stress that triggers to intensify the electric field across its dielectric, that is oil and paper. The amplified electric field has then forced to undergo a rapid process of orientation, polarization mechanism within the dielectric molecules. The energy dissipated during this process converts into localized heat generation, that is dielectric loss, and that leads to increase the temperature of the dielectric material. A cycle of thermal runaway, once being started due to electrothermal stress, that triggers an uncontrolled cycle of lowering the electrical resistance of the dielectric material. A cycle of thermal runaway, once being started due to electrothermal stress, that triggers an uncontrolled cycle of lowering the electrical resistance of the dielectric material. That's why it is important. However, a lower resistance allows more leakage current to flow through the dielectric, causing to generate exponentially more heat, further reducing the resistance in a self-accelerating cycle that makes the dielectric material much more conductive. Due to have a continuous heat dissipation mechanism loop that causes irreversible breakdown of molecular structure within the dielectric materials, transforming a permanent conductive path that results in a direct short circuit. As the thermal runaway in oil paper insulation system is one of the most highly critical self-reinforcing uncontrolled feedback loop. So,
Probable causes with comprehensive guideline must be taken care of during design of high voltage power transformers. Again, I repeat, as the thermal runaway in oil paper insulation system is one of the most highly critical self-reinforcing uncontrolled feedback loop. So, probable causes with comprehensive guideline must be taken care of during design of the high voltage power transformers. When cellulose and transformer oil share a composite dielectric system, the discrepancy of their dielectric constants inherently cause an uneven distribution of the electric field. Another important point. When cellulose and transformer oils share a composite dielectric system, the discrepancy of their dielectric constants inherently cause an uneven distribution of electric field. It is as because from the fundamental expression, that the distribution of electric field within the dielectric materials, that is internal. It is as because from the fundamental expression where the distribution of electric field within the dielectric materials is inversely proportional to their dielectric constants. Both insulating oil and cellulose paper, act as extremely poor electrical conductors, excellent insulators, rather, but their conductivity values that are to fluctuate dramatically depending on temperature, moisture content, and aging criteria. In power transformers, these two insulating materials would have to act as a series dielectric arrangement. From the basic characteristics of an oil paper insulation system, the transformer oil typically exhibits higher conductivity and lower permittivity than the solid insulating paper. From the fundamental laws of electrostatics, for layered dielectrics like oil impregnated paper, the electric fields that are to distribute themselves inversely proportional to the material's permittivity. Again, I repeat, from the fundamental laws of electrostatics for layered dielectrics like oil impregnated paper, the electric fields that are to distribute themselves inversely proportional to the material's permittivity. In case of transformer, as the surrounding oil has a lower relative permittivity, dielectric constant, then the oil impregnated pressboard and cellulosic paper. So, in this series dielectric arrangement, the electric field is disproportionately forced into the oil spaces. Again, I repeat, in case of transformer, as the surrounding oil has a lower relative permittivity, that is dielectric constant, than the oil impregnated pressboard and cellulosic paper. So, in this series dielectric arrangement, the electric field is disproportionately forced into oil spaces. Therefore, electric fields naturally concentrate in the oil gaps. Therefore, electric fields naturally concentrate in the oil gaps. Any sort of voltage spike that breaches a transformer's operational limits, these gaps are become electrothermally overstressed Any sort of voltage spike that breaches a transformer's operational limits, these gaps, these oil gaps rather, these gaps are become electrothermally overstressed. These overstressing oil gaps can lead to partial discharges which erode the fundamental characteristics of the dielectric system. So, this phenomenon makes the oil to become typically a weak point of the insulation system. But such criteria has rather to shield the solid pressboard and cellulosic paper insulation from the direct impact of the extreme electric stress. The lower permittivity oil is always to experience higher electric field stress and is often be the first location for partial discharges or microbubbles to form. I repeat, the lower permittivity oil is always to experience higher electric field stress and is often to be the first location for partial discharges or microbubbles to form. Particularly in a composite dielectric system, there must have a discrepancy in their dielectric constants, which inherently cause an uneven distribution of electric field. Under the exposure of non-uniform electric field as developed in a composite dielectric system, the higher electric stress in the oil produces the dielectrophoretic forces. Dielectrophoretic forces. These forces act on the uncharged polarizable particles such as moisture droplets, cellulose fibers, or sludge suspended within the dielectric oil, pulling them toward regions of the highest electric field intensity. It is as because the highest electric field intensity is always in the material with the lower permittivity. It is as because the highest electric field intensity is always in the material with the lower permittivity, that is oil or within the oil gaps. The direction of the force depends on the polarizability of the contaminants relative to the insulating oil. The direction of the force depends on the polarizability of the contaminants relative to the insulating oil. Moisture and contaminants generally have higher relative permittivity than that of the oil. So, they have to experience positive dielectrophoretic force, positive dielectric force, dielectrophoretic force, and that causes to drive them toward the microvoids or gaps within the paper or oil. As the particles are drawn into regions of high electric stress, as the particles are drawn into regions of high electric stress, they align end to end to form bridges or conductive chains in between the interfaces of oil and paper or pressboard. Moisture significantly increases the paper's conductivity, potentially causing localized field concentrations over time. Depending on the level of permittivity, the distribution of electric field in the oil will be roughly double than that of the paper for the same thickness, making the oil more susceptible to partial discharge or breakdown if not properly designed. Again, I repeat, depending on the level of permittivity, the distribution of electric field in the oil will be roughly double than that of the paper for the same thickness, making the oil more susceptible to partial discharge or breakdown if not properly designed. Perhaps it is rather to understand that the constant occurrence of interfacial polarization in high voltage transformers is an inherent consequence of their heterogeneous oil paper pressboard insulation system. That is the reason interfacial polarization is much more detrimental so far the high voltage transformers is concerned. High voltage transformer is concerned. Specific technical reasons behind the occurrence of constant interfacial polarization in high voltage transformers. Mismatch of dielectric properties. Number one. A. Discrepancy in relative permittivity. Transformer oil, impregnated kraft paper 4 to 4.5. Transformer oil, impregnated pressboard 3.5 to 4.5. Transformer oil, mineral or ester 2.2 to 2.5. B. Discrepancy in conductivity. Transformer oil, that is mineral or ester, features significantly higher electrical conductivity than solid, dense cellulose insulation. Number C, flux continuity. Maxwell's equations specifically dictate that the normal component of the electric flux density is only continuous across an interface between two different media if there is no free surface charge present at the boundary where to separate two media. Boundary adjustments. D. At the interface between two different dielectrics that should have the different boundary conditions, which thus to dictate how electric fields behave to conserve flux. As the dielectric constant in each region is different, so the normal component of the electric field is discontinuous. However, to maintain physical laws across an interface, the total electric fields instantly adjust their magnitudes at the interface to conserve the flux continuity. Again, I repeat, however, to maintain the physical laws across an interface, the total electric fields instantly adjust their magnitudes at the interface to conserve the flux continuity. This behavior is caused by maintaining specific electrostatic boundary conditions. Number two, charge accumulation mechanism. A. Current asymmetry. Such phenomenon is caused by difference in conductivity and permittivity between the transformer oil and the cellulose pasteboard and paper. This creates an imbalance in how charge carriers flow through the composite insulation. This creates an imbalance in how charge carriers flow through the composite insulation. However, the difference in conductivity causes more electrical current to flow through the oil than through the paper. interfacial trapping. Migrating free ions inside the liquid oil travel toward the boundary but cannot easily penetrate the tight cellulose matrix. That is crystal lattice of the cellulose. Charge carriers, electrons and ions are thus to accumulate and become trapped at the boundaries between the solid and liquid dielectrics, hindered by varying trapped energy levels. Space charge formation. The trapped charges pull together at the interface. Trapped charges pull together at the interface, forming a dense layer of strong localized space charge zones within the bulk. Again, I repeat, space charge formation, most important. The trapped charges pull together at the interface, forming a dense layer of strong localized space charge zones within the bulk. Last one is field distortion. This accumulated charge layer creates its own localized electric field, that is space charge. This accumulated space charge layer creates its own localized electric field, severely distorting the original macro level field distribution. This dense localized accumulation distorts the originally uniform electric field, accelerating insulation aging and increasing the risk of partial discharge or voltage breakdown. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Please share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.